this equation, because this whole chapter of bending equation is based on this single equation. So let us be understood this equation on this tabletop. The equation is m over I is equal to f by y is equal to E over R. M is nothing but moment of resistance in terms of kilonewton into meter or Newton into mm. I, it is termed as moment of inertia. Properties of a cross section, the unit is meter raised to 4 or millimeter raised to 4. F, that is bending stress at a particular section distance from y, the unit is Newton per mm square or kilonewton per meter square. Y, that is the distance from neutral axis. Distance from neutral axis, it is in terms of m, meter or millimeter. E, modulus of elasticity, Young's modulus, property of a material, it is in terms of Newton per mm square. R, radius of curvature of a particular section of a beam, the unit is of millimeter or meter. So with this discussion, let us go ahead with the next one, and our intention is to prove the neutral axis coincides with centroidal axis. Now, the neutral axis of any transverse section of a beam is defined as the line of intersection of the neutral layer with the transverse section. It is written by NA. Repeat once again. The neutral axis of any transverse section of a beam is defined as the line of intersection of the neutral layer with the transverse section. As we know that there is no stress at the neutral axis, the stress at a distance y from the neutral axis is given by F is equal to E over R into y. So, if we can refer the following cross section, rectangular cross section of a given beam, let us consider a small layer of a particular layer at a distance y from the neutral axis NA, then dA is the area of layer. Then force on this layer is equal to stress on the layer multiplied by the area of the layer. So force on the layer is F multiplied by dA. What is F? F we already found out, and see the previous slide, E by R into y. So if we replace the term F in this particular slide, then we got the force on the layer is E by R into y into dA. Now, total force which is acting on the beam section is obtained by integrating of the above equation. So, total force on the beam section we can achieve by integrating of the equation, that is integration of E by R into y into dA is equal to E by R, that is a constant term which comes out of the bracket, out of this integration sign, because E is the property that is known as the modulus of elasticity, R is the radius of curvature. These two terms are constant for a given section, and then these two terms comes outer side of the integration sign. So E is equal to E by R integration y dA. Now E and R are constant as I told, but for pure bending there is no force on the section of the beam. What we define the pure bending? Pure bending is defined as the zone where only pure bending moment is act. No force is acting. Hence, there is no force which is acting on the section. So, this total force on the beam section, that is the E by R integration y dA, that we have to equate it with 0, as no force acting under pure bending section, pure bending zone. E by R is constant, so only the term is remaining, means A into B is equal to 0. So either A part is 0 or B part is 0. Here A part, that is E by R, is non-zero because it is a constant term. So the none of the option which is remaining with us, that is E by integration y dA is equal to 0. It is a big significance. What is integration y dA? Integration y dA, let us be understood what is y. Y is nothing but the distance, perpendicular distance from neutral axis to one specified layer. dA, area of layer, it is represents as the moment of area dA about neutral axis. I will repeat my words once again. Y dA represents the moment of area dA about neutral axis. Hence, integration y dA represents the moment of entire area of the section about the neutral axis. But we know that the moment of any area about an axis passing through its centroid is also equal to 0. Remember this verse once again. Moment of any area about an axis passing through its centroid is also equal to 0. Hence, neutral axis coincides with the neutral layer, that is, centroidal axis of a section gives the position of neutral axis. I will recorrect the statement once again. The neutral axis coincides with the neutral layer as well as the centroidal axis. Hence, the centroidal axis of a section gives the position of the neutral axis. I wish you have understood this theory also. Now, let us go ahead with the concept of section modulus. What is section modulus? How we can find out this section modulus for some of the regular shapes like rectangular section, square section, circular section, hollow rectangular section and hollow circular section. So before we proceed with the solution of problems for this particular chapter, let us be understood the concept of section modulus. What is section modulus? Section modulus is defined as the ratio of moment of inertia of a section about the axis to the outermost layer from the neutral axis. That means Z is equal to I by Y max. It is the ratio of moment of inertia to the maximum distance from the neutral layer or neutral axis. In short, it is defined as Z is equal to I by Y max, while I is the moment of inertia, Y max is the distance of outermost layer from the neutral axis. Let us be understood this Y max, what it means. Please come to the table top. if we are taking one rectangular section, then this is known as outermost layer. This is also the outermost layer. If this line indicates neutral axis, then this distance is nothing but y max. This distance is y max. In other words, if the given section is not symmetrical, repeat the word, if the given section is not symmetrical, then this is y1, this is y2, and among y1 and y2 the maximum value is our y max. I wish you have understood the concept of y max. Let us go ahead with the section modulus. So m over I is equal to f over y. It is the basic bending equation. The stress F will be maximum when y is maximum. Interesting noting point over here. Refer. M over I is equal to f over y. The stress F will be maximum when y is maximum. So, if you can write m over I is equal to f max by y max, then m is equal to f max into I divided by y max, where this I by y max is referred as z section modulus. So, m is equal to f maximum multiplied by z. Here m is the moment of resistance offered by the section, that is, it is maximum bending moment. Also, moment of resistance offered by the section is maximum when the section modulus is maximum. Hence, the section modulus represents the strength of the section. Remember this word, that section modulus represents the strength of the section. Now, let us we are deriving certain equations for the section modulus for various shapes. Let us we start with the first one, that is rectangular section. A figure which has been drawn, width is b, depth is d, and distance from the topmost layer to the neutral axis is d by 2. As such, the given section is symmetrical about x-axis and y-y axis. So, at our case, the y max, that is the distance of the outermost layer from neutral axis, is d by 2. Why this d by 2? As such, this is symmetrical section. Now, we know that for rectangular section, I, what is the value of I for rectangular section? It is BD cube by 12, that we have already learned in the earlier chapter, that moment of inertia of a rectangular section is BD cube by 12. So, Z is equal to I by y max. If we replace the two terms, I by BD cube by 12 and y for d by 2, we can achieve Z is equal to BD square by 6. So, section modulus for rectangular section is BD square by 6. Now, let us we try to achieve for square section. Now, let us we go for square section on this particular tabletop. Now, given section is of square, side is A. The neutral axis passing through at the centroid of a given section, as it is a symmetrical section, this distance is A by 2. We know the value of I is equal to, the basic fundamental equation is BD cube by 12 for rectangular section. Here B is equal to D is equal to A. So if we can replace over here, we achieve A raised to 4 by 12. What is Y maximum? Y maximum is nothing but A by 2. Then Z is equal to I by Y max is equal to A raised to 4 by 12 divided by A by 2, and we achieve A cube by 6. So now you can visualize for a given rectangular section, no rectangular, sorry, for a given square section of side A, the section modulus Z is equal to A cube by 6. Now let us go ahead with the next section, that is hollow rectangular section. Refer the figure precisely. So let me draw the first of all a figure over here on a tabletop. This hatching means it is a solid part, and this central one, which is a hollow part, this thing has been cut off, taken out. So let